so now we're going to basically close out this chapter by looking at some general information concerning different elements and different groups in the periodic table. We're going to start off with a discussion of the noble gases. The noble gases are the elements that will be located to the far right of the periodic table in group 8A. All right, they're called noble gases because they are very stable. They all have 8 electrons on their outer shell, and as such, they have very little tendency to either lose, gain, or share electrons in any chemical reactions. All right. So as stated here, they very rarely enter into chemical reactions. In fact, only a few compounds of noble gases have been made, and these are usually the larger ones, the one further down the periodic table. And as far as I know, I haven't checked this lately, but as far as I know, nobody has been able to succeed in making any compounds containing helium or neon. So they are very stable, so stable that it has not been done before where these have combined with other elements to form a compound. All right. I want to talk about flame colors with respect to metals, right? Metals, we know, as we stated before, have lower ionization energies, right? And basically, whenever you have a particular substance, and this is true for metals, when they are exposed to a certain amount of energy, which promotes electrons from a lower energy level to a higher energy level, immediately what will happen is that those electrons will fall to the lower energy level and will emit colors or radiation of different colors, right? And this is true for metal ions for the most part. And that's because, as I said before, they have low first ionization energy. So basically, if you can excite these electrons in these metal atoms and ions, then what you're going to see is that the color that is given would be kind of specific to that particular element. So what you're looking at here are some pictures of a very simple experiment where you take a nichrome wire, which is an alloy of nickel and chromium, which is very inert, and you dip it in a solution containing these particular ions: lithium, sodium, potassium, calcium, strontium, and barium. And then you put it into a Bunsen flame and you see these different colors. So sodium will give a characteristic yellow color, potassium will give a characteristic blue color, and calcium will give a red color, and so on and so forth, right? And that is typically what will happen with these metals, because when the electrons are excited and fall back to lower energy states, they emit radiation which falls within the visible region of the spectrum, and that's why we see these colors. Now, elements with higher ionization energies, first ionization energies, usually require higher temperatures for emission. And when emission takes place, the radiation that is produced falls outside of the visible range, and therefore that's why we cannot observe those colors with our eyes. All right. So there's some limitation, in other words, when using a flame test to detect particular ions or particular elements. And that's why the flame tests are usually limited to metals and not non-metals. Okay, another thing I want to talk about is the fact that some elements are strong reducing agents and others are strong oxidizing agents based on their positions, relative positions in the periodic table. So we have to revisit the whole concept of redox. And if you remember, just to give a brief review, redox stands for reduction oxidation. Oxidation involves the loss of electrons, and reduction involves the gain of electrons. So basically, when something gains electrons, it is being reduced, and it is also acting as an oxidizing agent. And whenever something is losing electrons, it's being oxidized, and it's acting as a reducing agent. So first general statement here concerns the elements in group 7A. They tend to be very good oxidizing agents. And that's because halogens have a high affinity for electrons, right? And therefore, their oxidizing power generally falls in line with electron affinity. So basically, the higher the electron affinity, the higher the oxidizing power of the halogen. And when I say higher electron affinity, I'm talking about the more negative the value is. If you remember, the electron affinity values are typically negative, all right? And what you'll find is that the oxidizing power increases as you go from bottom to top of the periodic table. And that can be demonstrated with the reaction being shown in these pictures right here. So what is being shown here is a test tube, which is filled with iodide ions. And this person, whoever he or she is bubbling chlorine into this solution of iodide ions. And what happens spontaneously is the formation of a purple solution. And by the way, this is dissolved in a carbon tetrachloride solution right here. And that solution will be iodine, which forms a brown solution here. But when you dissolve it, when you add carbon tetrachloride to it, the carbon tetrachloride becomes purple, right? And that's because the iodine is more soluble in the carbon tetrachloride. Okay, so just to give you the equation for this reaction, the equation is Cl2 plus 2I minus to give 2Cl minus plus I2. I'm sorry, I2, not H2, I2. All right, so that's the reaction taking place. And in this particular case, the chlorine is acting as an oxidizing agent, and the iodide is acting as the reducing agent. And that's because the chlorine is above the iodine in the periodic table in group 7. All right? Okay, and you can, of course, figure out what will happen if you bubble, let's say, fluoride or fluorine into chloride ions and so on. Okay, so that's group 7A. Then when we get to the other extreme, or to the extreme left of the periodic table, what you'll find is that the elements in the S block region, they tend to be very strong reducing agents. In other words, they tend to give up their electrons. And that's because for these elements, their ionization energies, which corresponds to the loss of their valence electrons, would be very low. All right? So basically what that means is that the low ionization energy, especially the first one, means that the metal will give up its electrons to, let's say, hydrogen in water, and the result will be the formation of hydrogen gas, right? So that is being demonstrated in these pictures here. So if I'm not mistaken, yes, I am correct. The first picture here shows you what happens when you add potassium to water. That's a very violent reaction. In this case, it's a small piece of potassium that is added to the water, and you're going to get a very strong reaction. Exothermic, produces a lot of heat and light. And then this picture here shows you what will happen when calcium reacts with water. Now, this is not as vigorous, all right? But the reaction takes place. It's also a redox reaction where the calcium will give up its electrons to the water to form hydrogen gas, which will be formed over here as well, all right? And then the last one is magnesium in water, and you'll notice that the magnesium here is not reactive in water, at least cold water, but the reaction will take place if you heat the water and the magnesium combination. Again, you're going to have the redox reaction taking place. So the equation for this reaction here, I'm just going to use potassium as an example, is potassium plus H2O to form potassium hydroxide and hydrogen gas. So that's a reaction taking place. And of course, to balance this, we need a 2 here, and we need a 2 here, and I think, and we need a 2, we need a 2 here. So that's it. I'm just checking to make sure it's balanced. 4, 4, 2. Oh yeah, okay. So now it's balanced, all right? So that's basically what happens when we have these metals to the extreme left in the P block, I'm sorry, the S block region. They tend to be very strongly reducing. And as you go down the group, the reducing strength increases. So that's the reason why, for example, if you compare potassium to sodium, potassium will react faster compared to sodium because potassium is below sodium in group 1A. Okay, so now we're going to get into a discussion of the different types of oxides formed by elements. And they can be put into 3 categories. We have acidic, basic, and amphoteric oxides. An acidic oxide is one that produces an acid when the oxide reacts with water. And typically acidic oxides are basically molecular substances where you have a non-metallic element combined with an oxygen to form a non-metallic oxides, all right? Basic oxides, on the other hand, produces bases when reacting with water. And typically speaking, bases are most often metal oxides, right? So an oxygen combined with some metal will form a basic oxide, all right? So those are basically chemical opposites in terms of their behavior. And then we have amphoteric oxides, and these oxides kind of straddle the lane or the border between acidic and basic. They can act as an acid or a base, all right? So I think we have some examples. Well, again, going back to this periodic table here, is showing you basically the type of elements that would form amphoteric oxides, and that's these right here: beryllium, aluminum, gallium, germanium, tin, antimony, bismuth, lead, arsenic. These tend to form amphoteric oxides. They form oxides which behave as both acids and bases. Acidic oxides, on the other hand, tend to be, as I said before, non-metallic oxides, and basic oxides tend to be formed by elements in the S block region, and some others as well, but mainly in the S block region, with the exception of beryllium. All right? Okay, so that's basically it for this chapter. So the next video I'm going to post up would be based on chapter 9. All right? So please be on the lookout for that.